Let's look at this one again. Can you, now that you're expert, can you draw number 4 again? So, draw the region for number 4 again. Don't look at what you did before. Start over. You won't remember it. Start over. Draw the region that is expressed by number 4. That means you have a sheet of paper and something to write with. Everyone got the limits written down? I have to get my writing pad turned on. How do we do? Jonesy, can you tell me something? Something about this?
So I draw a line.
Okay. Which line?
X equals y over 2.
X equals y over 2. And is that steeper like this or more shallow like this?
It's more shallow like that.
Like this?
Yes.
X equals y over 2 is the same as? So, is that more steeper like this or more shallow like this?
It's more shallow.
Y equals 2x?
Oh, no.
Okay, it changes to, right? So y equals 2x, something like that. Okay. And then tell me something else, Ryan?
So I solved the upper bound
Okay,
in order to get an equation of a circle.
good. Okay, what circle?
X squared plus y squared equals 5.
Okay. X squared plus y squared equals 25. So that circle has center at? Where's the center of that circle? Origin with radius? You should have all found that. We'll see lots of equations like that. And that's equation of a sphere. We solve for z. It looks a lot like this. 25 minus y squared minus x squared equals z. And that's the top half of our sphere, right? So circle radius 5. Okay, something like that. And then this is, what do we do first? Do we do left to right first or top to bottom first, Fernando? Left to right, and we're going from what to what when we go left to right? Good, from the line to the circle. So we imagine our inside integral is for a typical y value, we go from left to right, and then bottom to top, right? And that's our dy. So then we accumulate one of those strips, and then we take all those typical strips and we accumulate from bottom to top. And it fills up that region, right? So we're talking about this kind of wedge, right? This pie piece right here. That's right in there, okay? And so what if I wanted, could I use a double, so does this integral find the area of that pie piece? What does the double integral find? Yeah.
Will that be 0 to 0 equal 5? Will that be equal to 5?
I didn't-
Or just for the y, will the y be bounded off also? Or like,
Are you talking about these bounds then?
will that be bounded anywhere?
Yeah, so this is saying left to right, so that's our like typical strip for any y. And then we take the first strip is at y equals 0. Where's that? So first strip, y equals 0. And where's that? The bottom. And then we're going to accumulate all strips up to y equals 2 radical 5, which is the y coordinate of that point. So, so then it accumulates all these typical strips all the way up to the top. Did that answer it?
I didn't think it was the top. So
Yeah, so it's to whatever this y value is, and that turns out to be the intersection of those two, is that y value. Okay, so my question was, what does this double integral find? What is the meaning of it? Yeah, Sandy?
It finds the sine volume of the function to the xy plane in that area.
Right, so we have to imagine now this function lives in where? Where does this function live? R3, right? It lives in R3. It's a surface, right? And so this double integral finds what? Sine volume of this surface, between this surface and the, from the surface to the xy plane, right? And it finds what? Sine volume, meaning difference of volumes. Wherever the surface is above the xy plane, it gives a positive contribution to that double integral. And wherever the surface carves below the xy plane, that's a negative, right? So it's sine volume. So my question is, can this double integral find area? And this is what we were talking about right when you were thinking about all your awesome spring break plans, like the last 5 minutes of class, Friday. So what did we talk about? Can this double integral, can we trick it to find volume? How? So what volume, what net volume or signed volume has the same volume as this area? That's the question, right? So if we can make this volume be the same volume as the numerical value of this area, then we tricked it to find area for us. So how do we do that? Remember?
Set the function equal to 1.
Right. So if we have the surface is just height 1 everywhere, then the volume is base times height. And base times 1 is just the same as the area of the base. Really important concept. Go watch the video again if you didn't catch that. If we set the function equal to 1, now we have a volume with height 1 everywhere. And that has the same value as the area of the base. And so we've kind of tricked the double integral into finding area for us, this area, this region. Okay, so now we want to talk about another way to do this double integral. So and if we did type 1, which would be bottom to top, left to right, what would the implication of that be? If we changed the order of this double integral and did bottom to top, left to right, then what would be the theme of that problem? What's that? It would be 2 pieces, right? The top is split up into 2. So we'd have to add 2 double integrals to get the same result as this one double integral if we switch the order of integration. So you should see that because the top is split up, right? Bottom to top is different on the left side versus, or over here on the left side of the region versus more to the right side of the region. Okay, so we want still a third way to do this double integral. So we've talked about type 1 and type 2, what we're calling type 1 and type 2, but then today we're going to introduce a third way to do this. And you learned about this in Calc 2. Any ideas? In Calc 2, you learned about a different system that would be a good approach for this problem. No, it's not. We're not revolving it. That's like if you're revolving this thing. It's not revolving it yet.
Since it's a circle, can you use this polar?
Okay, polar coordinates. See polar coordinates. What are polar coordinates based on? Polar coordinates, what are the coordinates in polar coordinates? R, right? R is defined as distance from the pole in any direction, right? We're no longer dealing with horizontal and vertical coordinates. R is distance from the origin, or now what's called the pole. The pole is what we used to call the origin, but in In polar coordinates, we call it the pole. Distance from the pole, this is the pole, 0, 0. And then, what's the other coordinate? Theta. And that's our standard trig angle. It's the same trig angle that we used for what? Directional derivative, right? So, what? Angle measure swept counterclockwise from the positive x-axis. And that's the same theta we used for directional derivative, that we used for sine and theta, sine and cosine, that we used for trig, right? Okay, so this was y equals 2x. All right, so how would we, what is that in terms of our, so let's do this first. So this is x squared plus y squared equals 25, that's easier. So in terms of r and theta, if we're going to convert this thing into r and theta, we're going to change the coordinate system now from x and y into r and theta, what would the circle be? What defines, in terms of r and theta, what defines all points on the circle? Is that? What were you going to say? They both. You also? Yeah. R equals 5, right? Right? Because this is all points that are exactly 5 units from the pole. So this is r equals 5. Okay, and so then you can kind of see, if you remember what our relationship between r, x, and y are. So if that means that what, r squared equals 25. So here's one of our relationships between r, x, and y. What is it? X squared plus y squared equals r squared, right? And so if it's distance from the pole, that should make sense. That we always can have, for a point, we can always have a right triangle, and r is like the length of the hypotenuse, and x and y are the legs, right? So I can draw that here. X, y, r. And so we immediately see that what we just said here is that r squared equals x squared plus y squared. Okay, what else? So what else? This is our angle theta in polar coordinates, right? Our standard trig angle. So what does x equal? Lauren? R cosine theta, right? Because cosine theta equals what? Adjacent over hypotenuse. So x is going to be r cosine theta, and then y is? Well, that's easy if you know x, right? So here are relationships that bridge us between what? Polar coordinates and rectangular coordinates. So if you have r and theta, that's how you get x and y. If you have x and y, that's how you get r. What about theta? So what about theta? So let's just take a look at this example right here. Y equals 2x. So if y equals 2x, doesn't that correspond to all r values for a particular theta? Do you see that? So isn't that constant theta, and r can be anything? So what would theta be then? Or could you figure it out? What's that?
Tangent inverse of 2 over 1.
Tangent inverse of 2 over 1. So how'd you get that? Because you thought of?
I thought of x being like 1, and so I thought of triangle.
Yeah, so on y equals 2x, the ratio of y to x is always 2 over 1, right? That's the rate of change, right? The rate of change is always 2 to 1. And so then that angle would be arcsine. Arctan, sorry. So arctan of 2. So we just transformed this, and this, so this line here is theta arctan of 2. And this line here is, what is this? So we're talking, because we're still talking about the same region, right? We still want the same region here. So how would you define this boundary? What would that be? This boundary of our region? Theta equals 0. Easy. So we got theta equals 0, we got r equals 5, and we got theta equals arctan of 2. And that is another way to define that same region. We got the boundaries of it. So now how do we want to think about how do we want to think about setting up a double integral? So now our f, so now if it's that same function, f of xy, that's going to be f of what? R cos theta, r sine theta. So we need that function, our integrand, we need it, what, transferred or interpreted in terms of r and theta. Okay, so then the question is, you know, what is dA? Is it just dr d theta? And then what's the order? So we have some issues here, right? So this is how we want to think about that. Got a little animation for you to think about double integrals. Okay, questions about what we've talked about so far? So transitioning from this thing being in either type 1 or type 2 in Cartesian coordinates to polar coordinates. And we got the boundaries. We got that down. This is theta equals 0. This is theta equals arctan of 2. And r equals 5 forms that same region. Now the question is, what does it mean to integrate in polar coordinates? What does it mean to do a double integral in polar coordinates? So let's take a look here. So ready? Here's the way we think of it, and then I want you to talk after you're watching this. Okay? Do it again. So there's some funkiness at the end there. Come on. All the way. Okay, so talk. So what is this showing about doing a double integral in polar coordinates? So there's that thing. Okay. And then here you go. Ready? Here it is again. Okay. Derek, what do you think? So what did you guys talk about?
What was the initial question?
What is this showing about integrating with respect to r and theta? Like in terms of what is our image of it going to be?
Well, it's just going from the bottom function to the top function,
Okay, so
and then sweeping across it with theta.
okay, so instead of bottom to top, because bottom kind of is like a lower y coordinate to a higher y coordinate, it's not going to be there anymore. So how can we kind of change that language? Yeah, like in to out, inner to outer, inside to outside, right? So closest to the pole, out, right? And so what is that limit of integration? Or what variable are we talking about there? This is r, right? This is the change in r. So first, we pick for a typical theta in the region, we're going to go inner r to outer r. Inner r to outer r. And then?
How far does this go?
Then change in theta. So starting theta, right? Starting theta to ending theta. So that's the way we imagine these polar double integrals. Inner to outer, starting theta to final theta, and we know that sweeps counterclockwise, right? We know that sweeps if we're going from lesser to greater theta. If it's a lesser theta to greater theta, which that's what we'll typically see, it'll go inner to outer in r, dr, and then theta goes from starting theta to final theta, which is normally a counterclockwise sweep. Yes, please.
Just to clarify, when we have the line going across from inner to outer, that represents not just a line, but it represents a three-dimensional, there's a function on top, it's representing a series of rectangles being added up.
Well, we never really said that with type 1 and type 2. So if we're just focusing on the limits of integration are how the region is represented in R2. So you don't have to do that, right? So, but yes, if you want to take if you want to look at the whole double integral, including the integrand, then you can think about it as a wall, right? As a wall that's coming across, and then we're sweeping this wall because it's going to be volume. But I'm just giving you this, just if you're focusing just on the limits, you can think about just R2. Yeah. But so, yeah, you're right. It's just, that would be a different way to think of it. Adding the third dimension. Okay, so then the last question is, what is dA? Is it just simply dr d theta? Do we just go dr and then d theta? So let's take a look at that. All right, so here's just a summary of what we said. So polar is that we're going to do inside function to outside function, inside to outside. And then theta 1 to theta 2, or starting theta to final theta, which we normally will be counterclockwise. So inside to outside, that's our dr, and then starting theta to final theta to cover the whole region, or create that whole region. All right, so we said the order is dr d theta, but then the question is, what is dA? What is a little bit of area in polar coordinates? Because theta is not distance anymore. Right? R is distance. X and Y were both distance. So it was really nice. We just, dA is just the area of a little rectangle, base times height. But theta is not distance, right? So dr d theta probably isn't right, because yes, dr is a little change from the pole, but theta is not measuring distance, right? It's dependent on how far you are from the pole. So let's do the math here. So this is what a little chunk dA looks like. And so our question is, what is the area of that little chunk? All right, so let's start with the easy thing first here. So first of all, let's do our angles first. What angle is this? So that's just, we're at angle theta. And then what is that? What would that be? A d theta, right? A little change in theta, right? So we're going to consider a little change in theta. Okay? And so then, and what is this distance here? That's our distance out to this little element. So our distance from the pole, theta is our counterclockwise angle from the x-axis, and now we're considering a little change of theta and a little change of r. So which one is the little change of r? Exhibit A or exhibit B? B. So the last question is then, what is this dimension, right? So this dimension right here is what we're going to multiply by dr to get dA. Is that length Is that d theta? Is that length d theta? No, because here it's a lot. If you put the dA way down here, then that length would be a lot shorter than if you put the dA out here. Do you see that? So as theta increases, that dimension is increasing. As r increases, that dimension increases for the same d theta, right? It's small here, but larger here. So what is that? That's, yeah, what were you going to say? Right, so this is right. This is like arc length of a circle. So if you have just any circle with angle, say alpha, and say radius capital R, so what we want to know is what is that length? What is the arc length for the part of a circle cut off by angle alpha? So I think, did Griffin say?
Yeah.
Was it Griffin? So was it, did you say R alpha?
R alpha.
Yeah. Okay, yeah, so this is the definition of alpha. The definition of alpha is actually defined as what? The arc length over R. It's a ratio. It's a ratio of arc lengths, right? It's a ratio of your arc length to R, so therefore your arc length is R alpha. So circular arc has length R alpha. So what will our little circular length be there? So what's our radius and what's our angle? So our radius is R and our angle is d theta. So dA equals? Is it dr d theta? We need an r in there too, because that d theta is not the right length until you multiply it by r. When you multiply d theta by r, then you actually get this little arc length here, which was going to change based on your r, right? It's going to be smaller down here and bigger out here. So that's why. So we know the order is dr d theta, but to get that dA, we need r times d theta. So what's going to happen? We've got it now. So because we're going to do, we got our f in terms of r and theta. We might have to switch that from x and y, right? And so we're going to have what? R comes first. And r could be a function of theta, right? So these r's are functions of theta, which we could use what's up here, say h1 and h2. And that's our dr, right? Inner function to outer function. The blue function to the red function first for a typical theta. And then? And yeah, I'll write theta 1, theta 2. That's or in this case, alpha to beta. But this needs to be dA, right? It needs to be dA, so we need an R. So what happens to the R in these problems? So R came to the table with dA, right? It came to the table with dA, but then what's going to happen to it? It's going to be integrated. It's going to link up and multiply with our function. So the reason we have it is because of dA. But then when we solve, and we're going to actually do antiderivatives and integrate this thing, that R then is going to join up with the function and multiply by the function. Do you understand? So it came from the dA, it ends up with the f. It came along with the dA, it ends up multiplying by the f, and you're gonna have an extra r multiplied by your function when you start solving it, like doing antiderivatives. Okay, so go ahead.
This extra r, it's always just going to be a number?
No, it's changing, right? It's our variable. R and theta are variables in this situation, right? So as we integrate from here to here, and we're basically accumulating these dAs, so these dA, so this dimension of this dA right here is a lot smaller than that dimension of this dA up here. So the dA, for a given theta, dA depends on how far you are from the pole. That's why that R is there. Is that better?
Yeah.
Okay, so that's part of the dA. But then, that dr then multiplies as a variable R. It's changing quantity, multiplies into our function of R and theta. Okay, so before we actually do some double integrals, let's practice setting up the regions, right? So given regions, can you come up with the limits? So can you come up with the limits of R and the limits of theta? So I've got some practice problems for you for that. So these, do you see the dotted lines? Yeah, good. So the dotted lines are just integer values, okay? So every dotted line is just an integer. And then all important angles are multiples of pi over 4, okay? So all the important angles are multiples of pi over 4. Although in future examples, you could have any angle, but I haven't given you any numbers here. So everything's in terms of pi over 4. And so what all you're doing for these is coming up with, so for a given function, we know we're going to do f, r, dr, d theta. And for each one, you're coming up with the 4 limits of integration that will define the region. So we'll call this one A, B, C, D. Okay, I'm going to take attendance while you guys work on those. Is the task clear? If you're stuck or you need help, you're making progress or you're getting help, right? You're making progress or you're getting help. Did you get the first one? So what is R? What's our R goes from what to what? It's our starting R and our final R. That's what the inside limits would be. Okay, Sarah, what is it? Yeah, so R starts at 0, and so for all theta, right, you see that R starting at 0 and goes to, no matter what theta is, it's not really a function of theta, it's just, it's always goes out to R equals 2. Okay? And then what about theta goes from what to what? Caitlin? She went 0 to 5 pi over 4. Agree? That's it. So that's A. Questions on A? All right. So yeah, so these are going to all these examples because everything's constant, right? So the R's aren't functions of theta. They're just constants, but that we'll see a lot of those. Okay, next one. Let's see. Here, Trevor. How about R?
For B?
For B.
1 to 3.
1 to 3. So starting R inside to outside, 1 to 3. Agree? And?
2 pi over 4 to 4 pi over 4.
Uh-huh. And what's 2 pi over 4?
Like pi over 2. Yeah, and you're just simplifying, right?
Agree? Everyone agree? All right, next one. Inside to outside, starting angle to finishing angle. Did you get it? Then? 0 to? 7.4. And what was this limit for the R? 0 to? 2. Everyone agree? Okay. Finally. Lauren, you want to do this one?
Radius from 2 to 3.
2 to 3.
And
negative pi over 4 to. Good. Agree with that? What?
Can we just write the root pi?
What do you want to do?
Can we just write the
Okay, so could we just do 0 to pi because it'll be the same area? So can we just go, if we did 0 to pi, we'd get the same thing, but it'd be all above the y-axis. Can we do it?
No, we're getting
So yes or no? What are you guys saying over here?
These ones I feel like yes you can because they're constant. So like other ones they might change if it's a.
Okay, that was a vote for yes.
Oh, we don't know what f is changing with respect to r and theta.
Okay.
So it could be different.
Right. Remember, we're integrating some function f, some unknown function f, over these regions. So what f is over that region is going to be different than what f is over the. You see that? So when would it be the same? When would it be the same just to do 0 to pi, from 2 to 3 and 0 to pi? If what? Right, but how do we do that? Yeah, so right, if f were any constant, right? And if we want the area of this piece, then we would make f equal to 1, and then we'd be integrating dr d theta. Is that right? R dr d theta, right? If you want the area, it's just going to be the double integral of dA. So you still have the r. And when you do the first antiderivative, what will your antiderivative be? R squared over 2. R squared over 2. Antiderivative of r with respect to r. So this would give, when f equals 1, your dA is still r dr d theta, so you still have the integrand r. This will give area of the region. Well, it tricks it, right? It's still giving a volume, but with height 1 everywhere. It's still giving a volume, but with height 1 everywhere. Okay, questions on these? All right, so now let's look at an integral. Actual integral here. Okay, so we want to sketch the region. Now I'm giving you the integral. We want to sketch the region. And then, so 2 tasks, change. So what is this, type 1 or type 2? This is bottom to top, left to right, which is our type 1. So it's change the order to type 2 or dx dy, change the integral to polar coordinates and solve. And when we do that, we should get the same thing both ways, right? Let's hold off for solving to the end. Let's make sure, let's get the order right. So we're just going to hold off on the solving part, depending on time. We'll work on the solving last, okay? Do we have the region right? Should have the region by now. Is this the region that you got? If you didn't, then something's not firing. Something's not right. I didn't see a lot of nods. How many people got the region before I drew it? Most. Okay, good. Okay. That was part 1. So now to change the order, we're going to do what? dx dy. So x is going to go from negative 16 minus y squared up to 0, and then from negative 4. So yeah, so we have these horizontal strips. The bottom horizontal strip is negative 4, up to the top is 4. Okay, and then now, so our integrand stays the same, but this we can do because we're doing x first, right? If by changing the order, here's an example where, with respect to y, not easy. Some hard technique from Calc 2. But with respect to x, pretty straightforward, right? This is just the result of chain rule, right? You can just, you've got your x squared underneath here, and you've got x to the first up here. So that's a chain rule derivative, and you can undo the chain rule. Okay, what about polar? Look how easy it is in polar. R goes from 0 to 4, and from pi to 3 pi over 2. Pi over 2 to 3 pi over 2, thank you. All right, what does f become? X is r cosine theta over r times r d theta, which becomes just r cosine theta, right? So the r, so remember our r from our dA links into the integrand and multiplies in with it. That means that these r's can go away. Which one do you want to solve?
Polar.
Polar. Polar is easy, right? R is just r squared over 2. You got the cosine theta. You got all constant limits. If you have a question, catch me on the way out.